Right. Hello, everybody. My name is Jorg Brown. I work at Google with Chandler Carruth on the C++ programming language platform, and I personally specialize on RISC-V. Seriously? Okay, you'll be working on it. I'll just try this one for now. So, like Chandler, I'm obsessed with performance and optimization. And for some time, I've wanted to give a talk at CppCon, or rather, I've wanted to have given a talk at CppCon. And finally, I have something worth talking about. So there's a recurring theme at work, which is template compilation overhead. Sometimes there's a team comes to us wondering, complaining really, why their builds are so slow. And a few months ago, we switched from libstd C++ to libc++, and while that was generally a great thing, there were a couple of builds that refused to build anymore. And so a couple of us were tasked to go and figure out what's going on. And so this is basically the story of the journey to figure out what the problems were and help those people, and in the case of libc++, to help ourselves. So generally, when I see a compiler that's running out of RAM or going slow, you can just blame templates. It's almost always the problem. Like we give up to 10 gigabytes of RAM to a compiler, and you're not going to run out in any more effective way than misuse of templates. They're just such a great way to run a compiler into the ground. Before I go too deep into that, let me go into some background. First of all, just programming basics, bubble sort is not that bad as long as n is small. In fact, really not that bad. Bubble sort is optimal when n is 3. You can't do better than that. Likewise, there are a lot of templates where if you're not, and specifically it's mostly variadic templates that are causing the problem, as long as you're not dealing with many parameters, they're fine. The trouble is some people write some code with a small number of parameters in mind, and then it gets out into the real world and people are just adding more and more and more. So in one case we had software designed to be able to specify a number of hooks into some code that receives RPCs, and designed for to have maybe 15 or 20 hooks. Then you go into the real world, you look at people are complaining about things being slow. It's because they're passing 150 template parameters. So that's what this talk is really about, how to deal with that and make that efficient despite the magnitude. Note also it's kind of hard to measure sometimes when things are going well. You can't just start up a Unix tool and measure the amount of memory allocation before and after in many cases, because the test cases that you construct are just lost in the noise. And the real cases where people are doing real work and the compiler takes 5 minutes, consumes 10 gigabytes, there's so much data that you can't handle it. So what I'd recommend if you are going down this path and writing test stuff is in Clang, there's this nice -x Clang, -print stats. It gives you fine detail, exactly how many templates are being instantiated, classes, variables, expressions, all kinds of stuff. It's really useful to compare two side by side and make sure that the changes you're making are really effective and going in the right direction. And by the way, generally, like the two biggest uses of RAM inside of a compiler when it's taking a lot of overhead is instantiation of classes and instantiations of functions. Another thing to try, if you compile with the -g option, then all of the types that the compiler had to instantiate in order to build the things for the binaries that it's dumping out will be listed. Dwarf dump is a great way to look at them all. And I'll show you some of the things that were dumped out when I had to try that with the libc++ conversion. So let's get some more basics, just functions. Take a simple example, Fibonacci. This is one way to implement it. It is not fast. You've heard of O(n)² routines. This is the rare exponential routine. It's because it recurses twice for every parameter you call it, all the way until it back gets down to 0 or 1. But it compiles really nice and fast. So let's alter that. First, let's make the function constexpr. Turns out, this still compiles really nice and fast. Thing is, even though the function is declared constexpr, that doesn't mean it's actually going to be evaluated at compile time. It just means that it could be if it needed to be. So the second thing we need to do is need it to be. So we'll take the result of Fibonacci and sign it into a constexpr variable. Now the compiler has to execute it at compile time. This still works okay, actually. However, let's up that number from 16 to 27. And now it fails to compile with Clang. It'll give you an exceeding step limit error. Microsoft Visual Studio will compile it, but it'll take about 10 seconds to compile it. And if you up the number to 28, Microsoft will also give you failure. Interestingly enough, GCC, no problem at all. It takes less than half a second. And the underlying problem here is that constexpr functions not necessarily memoized. So during this 10 seconds that Microsoft is spending, they're computing Fibonacci of 5 and 4 and 3 and 2 hundreds of thousands of times. So one obvious solution to this is switch to a template. Template has a nice feature that whenever a template is instantiated, it always has to be remembered. And so you can do it this way. It's basically the same exact algorithm. This, if you try it, it will work except for one problem. Actually, as it's listed here, it will recurse 1,000 times and give you an error that's trying to instantiate Fibonacci of minus 900 and something. And it's exceeded its limit. And the reason is that there's nothing blocking it from recursing. The question mark colon does not block in template instantiation. So the way you solve that is you just add a couple of specializations for 0 and 1, and that will block it. And now this works, and it's nice and fast, but also it's a bit ugly, it's a little bit tedious. It's weird to have the loop termination occur outside of the class. So one of the first things I recommend, if you're doing this kind of thing, C++17 has this nice feature, if constexpr, and it makes this code a lot easier to read. So when it's instantiating this, it sees if constexpr, everything inside those braces will be checked for to make sure the syntax is valid, but it won't actually instantiate anything. Still, it's weird to do it exactly this way. Why am I instantiating both a class and, in this case, a member variable? It would be nice if there was a way to make a function be evaluated at compile time. So this is what I call the one weird trick. Stood integral constant is surprisingly useful over and over again. In this case, we'll instantiate this Fibonacci function, but instead of passing the function a parameter, we'll give it a template parameter, and then we'll just return stood integral constant with it. That will force it to become a type that's being returned rather than an integer, and thus will force the memoization to happen. This function will always be constexpr no matter how you call it. This worked great. So another interesting thing about this is you'll notice it's using an auto return type. Now it has to use an auto return type because the type that is returned by this function depends on the template parameter. And so if I tried to specify the function return inside of the constexpr line, that would be at least as big as the function itself, and worse than that, that's not a place that I could use if constexpr. So it relies on being able to use an auto return type. But again, there's an extra benefit, and that has to do with the function signatures, which also contribute to compiler overhead. So here are 3 different ways of writing the same function. You could declare it the standard way, you could template it so that it can take any type of string, or you could also template it, but this time use an auto return value. Of course, in the case where you're using auto return, you also have to specify what the body of the function is so that it can figure out what the function signature is. So these each get mangled. They get mangled in some strange ways. The usual C++ mangling doesn't need to mangle a return type because based on the parameters coming in, you always know what the return type is. In the second type, however, the return type depends on the template parameter. And because of that, the return type is part of the function mangling. And you can get rid of that overhead if you declare it by auto, because whatever the return type is just replaced by auto. Now, in this case, that's not a big deal. Stood string actually is a special case in the mangler. It consumes almost no space. But in other cases, for example, if you're using enable if, that can be a significant issue. For example, where we have routine just takes a template parameter, returns the same thing back. Pretty clear what the mangling would be. However, if I declare enable if for no other reason than just to say you can't call this if the type is void, what do you think the mangling is? I would have thought that there would have just mangled the return type stood string again. That's not what happens. It mangles the way that it computed what the return type is. I asked somebody who's a compiler expert exactly why it does this, and he told me after about 4 or 5 minutes. I think I've asked him 2 or 3 times, in fact. I still haven't quite got it. It's a very long story. It has to do with what if this particular inline function is compiled in 2 different environments where other things are possibly present in the type hierarchy or not. Anyway, the important thing is if you have an auto return type, you don't have to deal with this. Because if it's an auto return type, then the return type is just mangled as auto. And in this case, you can just put the static assert in, which is sort of my, what I wanted to do in the first place, and the error message you get is much nicer anyway. You get, the compiler says, this is it. It's clear, like, oh, the type you passed in is the same as void, you can't do that, fine. Much better than a very long template error message. So, that's the first part of the background. Let's just summarize. Inline, constexpr, and template. So, what's inline? So, the compiler calls something an inline function if you declared it inline. Any constexpr function will be considered inline, and any templated function will be implicitly inline, and any method function of a templated class or templated function inside of a class is also inline. Going back to the original thing where just you can declare functions inline or not, the problem there is people tend to be a little bit overzealous about calling things inline. They don't really realize exactly what it would mean if all of their inline functions were actually done inline. They don't realize that like 100K for a single routine is a bad thing. And the compiler doesn't like it either, so the compiler second guesses your declaration of whether something inline. So inline doesn't really mean inline. So what does it mean? Well, what it means is the linker. Okay, because an inline function that isn't inline could be generated in multiple translation units, what inline really means is when the linker sees these duplicate definitions of the same routine, it won't give you an error. That's all inline really means. The second thing is if you declare a function inline, but that translation unit has no need to actually call that function, or if every use of it indeed really is inlined, then that function will not be generated by itself anywhere. Going back, constexpr, again, it doesn't actually guarantee that something is evaluated at compile time. It just guarantees that it could be, if it needed to be, for at least one set of inputs. On the other hand, template instantiation is guaranteed to be memoized. A template will only be rendered exactly once. Going back to the previous example of Fibonacci, if constexpr and auto return types go very well with templated functions, as does stood integral constant. And finally, results may vary by compiler. As you saw, GCC was okay with one of the inefficient things that we had done. The other compilers were not. So, seems easy enough, right? So now, it turns out, if you look at a lot of the instantiations, what they very often come to is a set of code that is templated on a bunch of types. And the best way I can describe it is, let's talk about what it would do to write or what it would be like to write your own tuple class. So, start out with a definition. It's just a class templated on a bunch of types, right? So, At the base, if there's only one type being passed, then you just have one element, let's call it first. Of course, you need some way to be able to get at the element, and first is a private type, so we'll have to declare a friend struct called getter. We'll come back to that in the next slide because it doesn't fit on this one. And of course, all the tuples below that, we'll just also declare a member named first, but then we'll put all the rest of the information in the tuple as part of a tuple class that's instantiated on all of the rest of the types. All right? The getter class, in general, what it has to do is pick off the first type and throw it away so that it can instantiate on the rest of the types that are left. In this case, when you call get, it's going to just call the next getter down the road and pass it tup.more. And then the base class, all it's going to do is return the first. And then finally, the actual get function. Now, you may be wondering why I'm invoking stood tuple element rather than just using my own tuple code. This is because this is what I actually saw this team doing. They basically got this far in their implementation and then just punted and they said, you know what? Stood tuple element has a way to find the nth type. So we're just going to call it to figure out what type get should be returning. And we'll use that as a way to instantiate getter. So, what do you think of this code? Is it O(n squared? Turns out, even for this relatively simple code, it's worse. This is O(n cubed. For example, just the call, let's say we instantiate a tuple with 5 elements, we'll initialize them all, we'll return the first one, and we'll look at what symbols actually get generated. So the first thing is every one of those get calls has to generate an actual function call to get. The return type of get is generated by this call to tuple element that makes it into the mangling. And then each one of those has to recursively call into a getter. So every one of those lines is a different instantiation of the getter class. And each one of those getter classes has to instantiate itself with a variable number of arguments. So we have O(n squared functions generated, and each one of those functions has a signature size that is O(n). So that's where we get n cubed. So what can we do to make this better? So again, we'll just test this one line, get of 4. We do this get function, which instantiates these 5 getters in this order. Just by doing the most simple thing, we'll use an auto return type. Then we don't need the type parameter for getter. So the getter function becomes this, and the mangling for the get function becomes that. So it's a little bit better. And because we're not, instantiating, well, it still doesn't solve the problem. So the question is, can we avoid having to call all of those getter routines? Well, remember when I said that one weird trick, stood integral type? Stood integral type also works really well with function overloads. So rather than instantiate the rest of the tuple, we'll actually inherit from the next tuple down. And that allows us to directly call all of the member functions of all of these tuples. Then we'll insert an extra routine called get. And get will take a parameter, which is an integral constant, according to however many types are in the tuple at this point. And then finally, our get routine, when it wants to call one, it has to just figure out, okay, what's the function signature of the get that I want? So it takes basically, number of types it has -1, then subtracts the particular tuple we're interested in, calls get, and then we allow function overload resolution to pick exactly the get function that we want. Now in this case, it doesn't quite compile. You'll notice we have to use the get from our superclass get function as well as the new one we're defining for each of our tuples because we want to use whatever one is appropriate. But that also means that the base class, which in this case is empty, it also needs a get. So we'll add one, and even though it's never actually called, it just that the point is we have to have something for the using function to return. So, does this work? Yes. Now, the auto-get function, which is still as long, exactly calls directly down to the get that we want. But it's still O of n squared to instantiate this. There's a lot still going on, and at the base level, the fundamental problem with any of these is that you're only picking off one type at a time and then instantiating for the rest. So that's a fundamental problem you have to solve. My tuple ABC interprets from BC, which inherits from C, and in this case, it also inherits from the my tuple with no parameters at all. And then if you construct a my tuple of A, B, C, D, now you have to instantiate all of those, none of which are an exact match for any of the tuples that you've already had to instantiate. So what we really need is a way to inherit from each type individually. Fortunately, C++ allows us to do that. So we're going to create a leaf node, which is separate from our normal tuple. And it's just going to hold one individual value, no more. And I'm going to step back for a moment. I'm also going to show you what the constructors look like, because it turns out that one of the other big problems with the previous slide and the previous way of doing things is that to construct one of these actual tuples, you have to call first the constructor of the topmost tuple and give it, say, 150 arguments. That function constructs exactly one thing and then passes 149 arguments to the next thing down the road, and so on and so forth. This is just a demonstration that it becomes much cleaner because each individual leaf node only has to deal with constructing itself. So, back to the second definition there, this my tuple now inherits from my tuple of T ... So now, in the case of 150 types, you're inheriting from 150 my tuple leaf objects. But the constructor, we can actually get it to instantiate my tuple leaf, forwarding one argument at a time to each individual leaf object. And so the actual instantiations there on the bottom, we still have the problem of how on earth does get work? We need some way to figure out exactly what my tuple leaf to dispatch to. But there's a bigger problem here, which is if there's any one of these types that's duplicated more than once, like if you want a my tuple of int, int, this doesn't work because it tries to derive from two my tuple leaf of ints, and you can't derive from the same class twice. So we need some way to add an identifier into each one of these tuple leaves. So I've added this here. And so the idea is instead of just instantiating on char, short, and int, we'll also pass some identifiers 0, 1, and 2. And then instead of my tuple leaf of T ... there'll be my tuple leaf of index, T ... And the C++ knows how to take one index and one type in every tuple leaf that instantiates. I'm going to back up, by the way. You may notice that the constructor calls are gone. That's just to save space so that everything fits on the slide. Now there's one big problem with this, which is that template specialization, you can't have multiple variadic sections. So we need some way to solve that problem. Remember stood integral constant, the one-word trick? Well, there's a similar thing, stood index sequence. So if you go to the bottom, we'll instantiate my tuple with a single type that incorporates all of those indexes. And then we'll use template specialization to be able to take those indexes and pluck them out of the index sequence that's coming in, and then use the other syntax we're using, my tuple leaf of index, T ... starts working. So this works, except for get, and we'll get to that in a moment. In fact, we'll get to it right now. So in the leaf object, we'll now specialize the leaf according to that index that comes in. Again, we'll use using my tuple leaf of index, T ... get ... And then the actual top-level tuple, when its get gets called with an actual index parameter, I, will make a type, std integral constant, with that, and call get on that. Then function overload resolution will magically go and pick the exact get routine that we want and return the thing that we want to get out of get. And this actually works. I'm going to step back for a moment because I know a lot of you do not necessarily have access to a C++17 compiler, and this technique is applicable even in those cases. So actually, there's a bigger problem here I want to fix first. My tuple, before we were actually passing a std index sequence in, we really want that to be automatically generated. So we'll add an extra level of indirection. We'll take my tuple and instantiate it based on, it'll basically take the incoming types, calculate how many of them there are, pass it to a function called std_make_index_sequence. That becomes the first parameter, and my tuple can use that. Of course, this works except for one little detail. If you happen to want a tuple whose first type is itself an index sequence, I don't know why you would want to do that, but if you did, this won't work. There's an easy workaround. Just my tuple becomes my tuple impl, and then my tuple itself just becomes a using declaration, and the using declaration is the thing that automatically builds the index sequence of the appropriate size to call in. Now is where I was going, where this is C++17, it relies on the using declaration, which is a C++17 thing, unfortunately. So if you didn't have that capability to use that index, we're going to have to do something different. In fact, fairly a lot different. First, let's do a bit of a hack. Let's take the get. Instead of saying get of 1 or get of 2, we'll ask our users to pass get of 1 comma short or get of 2 comma int. So we're just going to add this extra parameter, and then the get function will take this, which is the reference or the pointer to the tuple itself, and we'll cast that to a mytuple leaf given I and t type. Then we'll have the actual leaf node that we're interested in, and then we can call the get function on that. This is not terribly good. Nobody wants to actually have to specify the type, but maybe we can deduce it. So when you call a function, and it's a templated function, it can often deduce the type of your arguments. Well, it's better than that, actually. If you call a function and you say, not just something has a type t, but say a vector of t, it can deduce, oh, okay, t is the type inside that vector. In particular, if you call it with mytuple leaf of 1 comma something, it can figure out what that something is. And so in this case, we have the function get, and the first thing we'll do in order to calculate which leaf is we'll call this function getLeaf, templated on I, and then getLeaf will look at this coming in and say, well, okay, this is a mytuple, that doesn't correspond, but this inherits from a lot of mytuple leaves, and one of those mytuple leaves has a particular index, and then it can deduce what the t-type is, return the appropriate leaf back, and then get works. Now, you may be thinking at this point, well, we don't really need this get function within the leaves anymore, which is true. We can just have the mytuple leaf contain nothing but value, and once we've called the get leaf function, we can just pull .value out of it directly. So this is great, but this still requires C++14. Let's go one more step further. Let's make this work on C++11. What if we can't deduce the function return type? We can't use an auto return. So in the case of getLeaf, it's pretty clear what it's going to return. So that just becomes my tuple leaf of I, t type. The get is only slightly harder. We can just call decltype of get leaf. Let get leaf do the expensive determination of exactly what the type needed is. And then that works back. This has worked great. Technically, this is still not C++11 because std make index sequence and std index sequence are not in C++11, but there are many open source libraries, including Appsel, that have their own definition of the make index sequence and index sequence that will work on C++11. So, yes?
So we're using auto as a return type, and we've talked about enabling. How do trailing return types interact with that?
So the question is, we're using auto here for return types. How does trailing return type syntax work with this? And basically, the benefit of using auto doesn't apply to a trailing return type, because the whole reason for removing the return type is so you can do some calculations based on based on named parameters. So it's basically that whole big thing of whatever the trailing return type gets mangled into the function signature.
Thank you.
So let's move on to case study number 2. This is libc++, looking at all the debug symbols, which were so voluminous that something wouldn't build anymore. And this is actually one of the causes. Std is same. And you think, like, how can something this incredibly simple cause any kind of a problem whatsoever? And the answer is, when I looked at the debug symbols, I saw a bunch of these. Now, this is just what you can do with char, int, float, and double. You can imagine in a program that has many more types than this. This is much, much, much longer. Like, what the hell is going on? Why is this? And the answer is that, well, actually, back. So the answer is that this ends up instantiating an is_same class for every possible combination that you actually pass to it. The compiler actually constructs a memoized class. It actually ends up saying this is what a constructor might look like, this is what the destructor does, whether or not it has an implicit copy constructor, whether or not it can do move construction. It's really surprising all the work that the compiler does on a completely empty class. So one way to make this better, let's have a little wrapper class. And the wrapper class will have 2 functions in it. One function will take the exact same wrapper class as an argument. The other function will just take a void star. So in previous case, where you would have called std is same type 1 type 2 : value, in the new code you would write wrapper of type 1 : is same. We'll take null pointer, convert it to a wrapper of type 2, and that will call either return true or return false function. And this is tedious, sure, but it only ever instantiates 2 functions per type, and it only instantiates 1 type per, or 1 wrapper type per type coming in. So it's still a fair number of classes and types. If you work down this road, we can actually do a little bit more of a win. We can make a wrapper base class that does the same thing, because is_same is always exactly the same for each one of these functions, or each one of these classes. And then the new function is just is_same inside of the wrapper. We can also write a little using clause that says is_same is going to be, again, one little trick, std interval constant, a bool, comma, and then the fancy expression with the wrapper. Std interval constant of bool, comma, true or bool, comma, false happens to be exactly the type that the actual std is_same function returns. So this is a perfect match, and the code comes out exactly the same either way. But now it instantiates far fewer. There's 1 wrapper function for any type, and 1 function inside of that wrapper class for each of those types. So more clearly a win. An even better example, turns out, std conditional. This is also surprisingly simple. Like, how would this be a problem? Well, it turns out that even though our application code didn't call std conditional a whole lot, Turns out the standard library within itself calls to conditional a huge number of times. Like the most common example being inside of std unique pointer, it has to figure out whether or not it actually needs space for an allocator, and uses std conditional to do that. And so look at the debug symbols, and there's std conditional of true, char void, true. All is just filled and filled and filled. So how can we fix this? Turns out, rather than templating conditional on all three at the same time, we could template conditional on just one. And then inside of that struct, we use a using declaration to pick out which of the other two classes we actually want. And in fact, there was actually a similar fix to this as a result of our investigations, was checked into libc+ about 3 months ago. And the great thing about this is that there's only 2 conditional classes that ever get generated by this. Obviously, conditional of true, conditional of false. There is no overhead of the using declaration at all. It just completely disappears. There's no type involved. So, another interesting one, std add const. We declare this. It does the same thing that all of the other type classes do, where first we define the class, and then add const t uses that class to figure out what type it's going to return. This wasn't really a big burden. Add const isn't called that a whole lot. However, it can still be improved because rather than having using add const t depend on instantiating the add const struct once for each type, we could just make add const t be equal to const t, right? So I tried this out, picked a reasonable little binary, tried to build it, and some of you have seen this guy before. This is Hiram Wright. He made an offhand comment which has become Hiram's law, which says, with a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by someone. So what's going on here? Well, let's take a really simple case, right? We'll have our new definition here. We'll declare a new routine called nop, which for whatever reason takes the template parameters passed in, adds const to it, and then does whatever it does. And we'll call it, in this case, we'll just call nop of I. Now, because the using declaration of add const t, in this case, is just const t, the compiler sees this call to nop being passed an integer and says, well, okay, I can figure out that that's t has to be an int in that case. No problem. Well, it turns out in the current actual definition where add const has to instantiate a class and then pick a type from inside of that class, it can't deduce what the type is. So with the original definition of add const, this wouldn't compile correctly, and it wouldn't so much throw an error due to this definition of nop, it's just that nop wouldn't appear in the overload set of functions that you could possibly be referring to. Now I think some of you are hearing that and thinking, well, that's kind of sad that the compiler can't figure it out. And then a few others of you are thinking, oh, wait a minute, so I can use this to remove my function from the overload set. I could use that. Which is why Hiram gets involved. So can't do that. Got a little more time. Just one more interesting weird trick that helps you reduce the O of n properties. In C++17, we have these fold expressions. And so very often when you're dealing with a long list of types, you want to apply a function to each individual type. In this case, we have a simple constexpr function which just tells you whether or not any one of those types is equal to a void type. That works in C++17, but how would you get that to work in C++11? Well, again, std integral constant and function overloads, they play really well together. So what we can do is we can find 2 functions OR. The first one takes an initializer list of interval constants bool false. Okay, so if you pass it an initializer list where every single entry in it is of type stood interval constant bool false, then it will return false. We'll have another overload of the function or, and in this overload, it will just take a stood initializer list of bool. This works because stood integral constant of bool, true or false, freely converts to the underlying bool. So when you call this function, you'll get this first one only if everything you passed is false, and you'll get the second one if any one of the elements is true. And the great thing is, this only ever generates two functions. So it's a nice way to solve that problem, bring an O of n squared thing back down to O of 1. And just for reference, this is how you would actually end up calling it in that case. You have a function where it's templated on a number of parameters, and you just call to the void, call type, instantiate each one, call it off to or, and it comes back with a true or false correctly. Finally, compilers vary and compilers evolve. A lot of this stuff, I think, in 2 or 3 years' time is going to be somewhat obsolete. It turns out that compilers don't compile the C++ language. They compile the general C++ specification, which also includes the libraries. So just like when you write memcopy, the compiler can actually avoid making the function call to memcopy because it knows what memcopy is defined to do. So if you copy memcopy of 4 bytes, it can decide to just pick up 4 bytes in a single read into a register and store it. Likewise, stood the same doesn't have to do all of the bad things that I'm talking about here. They could change the compiler and just say, we know what stood the same does, we're not going to bother to instantiate, as long as it doesn't have that weird Hiram's law issue of blocking overload resolution in certain cases. Having said that, that only affects the standard library. All of your code can still benefit from all of these techniques. Any questions? And thank you for stepping up to the mic.
I don't actually have a question. It's more of a comment. It was actually really enlightening to see the example with the auto return type, because like I mostly work on Windows, and on Windows in the MSVC ABI, the return type is not mangled into the function signature. And so I suspect, although I didn't even know about this trick in the Itanium ABI, but I suspect that this won't be a source of optimization in MSVC ABI. But I thought that was an interesting difference, and thought I would point it out. Yeah.
That means that there's probably a very subtle bug that MSVC has.
I mean, functions aren't overloadable on return type, but there are different semantics anyway. So, I mean, we can take it offline if you want, but there's issues where, like, when you have a dependent template type parameter in a function, like MSVC will think the types are identical, even though a conforming compiler will not, and it's like unfixable because of the ABI. But
yeah.
Anyway.
When you try to implement your own traits, so like the same or like just unary traits, do you have experience in how the compile time performance behaves of implementing it like the standard library does often, like with the struct, or the decltype, the Sweeney way with function declarations?
So there's 2 avenues of optimization that address 2 different problems that people have. One is that the compiler is consuming up too much memory. The other is that the compiler is taking too long. I know that these techniques definitely help with memory consumption. They tend to also help in time, just because if you're allocating a lot of memory, allocation isn't free. And depending on what your operating system is and how much memory you have, it depends on how free it is or how not free it is.
But is it true that like function templates instantiation don't have to be kept inside the compiler state during compilation for all in the entire compilation unit? So it could like forget about a function that was declared earlier, but it's out of scope. Right?
It's not so much that it's going to forget about the function. What it forgets about is that if this function is passed 2, that it returns the value 2. Mm-hmm. And that if it's passed 3, that it's returned the value 5.
Thanks.
Oftentimes when I'm implementing something that's actually lifting a value into the type system, I'm implementing something like types traits to use enable if. Have you found variable templates to be meaningfully impact compile times as opposed to building an entire type?
I have not, but in Gould's case, we actually turned on C++17 fully only the last month or two, so it hasn't had a chance yet to be an issue. Ask me again in a year.
Thank you. I was just curious when you showed the example of the enable if versus auto, if you know anything about kind of performance differences of sphenai via like an unnamed type name parameter, where the substitution failure is in the parameter pack, not in any of the return or function arguments.
So unfortunately, I didn't have a time to fit into the slides. But you see the if constexpr trick that I did for Fibonacci?
Yep.
In many cases, you would want to do something similar for if constexpr in actual template instantiations. And when you do that, using if constexpr is much, much cleaner, much more easier to read, and also much easier on the compiler than the various stood enable if variations that you might use.
Cool, thanks.
Thank you all for coming.